Hello Year 12, this lesson is on rates of change. So we'll be refreshing your memories about average rate of change and instantaneous rates of change. We're also going to be looking at applications to motion in a straight line with regard to position, velocity and acceleration. So if we think about a car travelling through a city, it's unlikely that it travels at constant speed. There's lots of different things that could happen to it. So in this distance time graph, a constant speed would be represented by a straight line. For example, going at 60 kilometers per hour down a rather empty straight road. Whereas if we're driving through a city, there's traffic lights to deal with, there's corners to turn around, there's people trying to park that might hold you up. So speeding up, stopping, for example, at traffic lights here, so this horizontal line represents it's being stationary, then it accelerates again, and so on. So while we don't know the speed of the car at any particular point, except when the car is stationary, we can work out its average speed over certain parts of the journey. A reminder that average speed is the distance travelled divided by the time taken. So when we're referring to our graph, we can find the average speed for any section of this journey by finding the gradient of the straight line that joins the start point of the straight line to the end point. So here's an example not necessarily involving a car, where we've got our curve here, the red part, and our blue line here is our secant. So for any function, f of x, which is my red line, the average rate of change of y with respect to x over an interval ab, that's inclusive, is the gradient of the line through the points A and B. So what we can say, and this should be a refresher from the previous chapter, the average rate of change for x in the interval a to b inclusive is f of b minus f of a over b minus a. Let's have a look at an example. I'll give you a moment to read through the information. Okay then, so to find the temperature at 6 p.m. At 6 p.m. our time is equal to 0. So we just substitute t equals 0 into our equation up here and we get 20 degrees. At midnight is 6 hours after 6 p.m. So at midnight t equals 6. So again we just substitute t equals 6 into our equation up here and we get 100 over 13. It's important that you write down this 100 over 13. That's the exact answer. We're not actually told to round our answer to anything here, so 100 over 13 should be what you provide as your answer, but just for our benefit to see what has actually changed with the time, it's a good idea to convert it to a decimal just to have a look at what it is. So it's about 7.69. So to find the average rate of change from 6 p.m. until midnight, I take the temperature at midnight, subtract the temperature at 6 p.m. divided by the difference between the times. You see here I've substituted my exact value for the temperature at midnight into my calculation. I have not used my rounded value. So again, it's important to have an exact answer, so negative 80 over 39, but then to understand what actually is going on, it's a good idea to convert to a decimal and round in this case, so negative 2.05 degrees C per hour. So that means the time is decreasing, which obviously we can see that's happening. To move from 20 to 7 degrees, it's got colder and it's getting colder at an average rate of 2.05 degrees per hour. Quick reminder that the instantaneous rate of change of f with respect to x when x equals a is f dash of a. So we differentiate and then you substitute the value of x at that point in. And just a note when it comes to explaining your answers in the context of the question, if our f dash of x is greater than 0, i.e. your gradient is positive, then f of x is increasing as x increases. If f dash of x is less than 0, i.e. we've got a negative gradient, then f of x is decreasing as x increases. So have a go now at these questions here. Sorry, I clicked forward a bit too quickly. You should be able to do 1 and 3, for example, without a CAS. It would be a good idea for you to have a go at this. Questions 5 and 7 and 8 and 10, I would thoroughly recommend CAS usage. Pause the video while you do this. Okay, quick reminder about motion. So displacement we represent by S. We also call it position and represent it by X. This is what your textbook does a bit more often. This is what my old textbooks used to do a bit more often, but you might see both, so it's good for you to know both of them. So that's where something is, where a particle is. Now we can differentiate our position function to give our velocity function. So v equals ds by dt. Alternatively, v equals dx by dt, depending on which one we're using. And then we can differentiate our velocity functions to give our acceleration functions. So a equals dv by dt. You might see this. I'm not going to explain it now. You will see this idea of a double derivative at later points in the course, so don't worry about it too much for now. So with that reminder, you can now complete the remainder of the questions from exercise 10b. Make sure you're checking your work as you go and ask your teacher if you have any questions. Thank you.